going to work a few more related rates problems here just to get some more practice. So we have in our first example, a metal cube contracts when it's cooled. If the edge of the cube is decreasing at a rate of 2.2, and that's the edge centimeters per hour, how fast is the volume changing when the edge is 60 centimeters? So we can imagine here that we've got this cube, looks something like this. And so a cube means all the sides are the same length. So we can call those S or maybe X, so it's X by X by X. We know our volume is going to be just X to the third. So let's see, the edge of the cube is decreasing at a rate of 0.2. So that means that dx dt, that's going to be one of those edges, it's decreasing. So that's going to be a negative 0.2. We want to know how fast is the volume changing, so we are looking for a dv dt. That's our goal. And this is going to be when an edge is 60 centimeters. So our value of x will be 60. Okay, starting with our volume formula, our v equals x squared, x cubed rather, we're going to take the derivative of that with respect to t, and so that's going to give us dv dt, and using our chain rule we'll get 3x to the second times the derivative of the inside function dx dt. So we know dv dt is what we're looking for, and the value of x is going to be 60. And our dx dt is going to be a negative 0.2. So some serious arithmetic here. We've got 360 squared is going to be 3600, and we've got this negative 0.2. Trying to see what we can do, anything nice and easy. I guess we could move the decimal over and get rid of one of those zeros. 3 times 36, 3 times 30 is 90, 3 times 6 is 18, so 90 plus 18 is 108 with another 0. Multiply that by 2, and I think we'll get a negative 2, we'll get a negative 2160, sounds about right to me, I hope. And that is our dv dt. And so that is going to be in cubic feet per hour. So our volume is decreasing by it's decreasing by 2,160, I think that's centimeters, not feet, cubic centimeters per hour. Okay, on to the next one. I'm going to move this a little bit up. So the height of a cylinder with a radius of 4. So we've got some cylinder here, and it's going to have a radius of 4. And it is increasing. What did I mean to say? The radius is increasing. So that wasn't supposed to be a capital I there. That's really just comma, is increasing at a rate of 2 centimeters per minute. Find the rate of change of the volume with respect to time when the height is 10 centimeters. So our volume of a cylinder is pi r squared h. You don't have to memorize that. The height of the cylinder with a radius of 4, so the radius is 4. And the height is what's increasing at 2 centimeters per minute. So the dh dt is 2. And we want to find the rate of change of the volume. So that's going to be dv dt is what we're looking for when the height is actually 10. So in this one, our radius is just a constant. So we can plug that in right off the bat. So we can say that our volume is going to be, the radius squared is 16 pi h. So From there, we can now take the derivative with respect to t of those. And so that's going to give us a dv dt is 16 pi dh dt. We can plug in what we know. The dv dt is what we're trying to find. And the dh dt is 2. And the height being 10 doesn't really make any difference in this case. So it'll just be a 32 pi. And since that's a volume, that's going to be in cubic centimeters. And the time, I think, was in minutes. Okay, let's see what we got on the next one. I'm going to make this a little bigger again. Okay, so we have a point moves along a curve in such a way that the y value is decreasing by 2 units per second. So dy dt is equal to a negative 2. And it didn't show, I don't know, I think, don't have the right software on my iPad to get what's on my laptop. So it's supposed to be a point moves along the curve y equals x squared plus 1. So let's see if we can, 2x squared plus 1, I guess. So the idea is we have this parabola, and so we know it's going to open up and it's going to be fairly steep like this. So this is our 2x squared plus 1 parabola. So the idea is that we imagine this particle is moving along this curve. So it's changing with time. So what we really have is a y of t is 2 times x of t squared plus 1, even though we don't write it with the functional notation. And we can see that reflected in the fact that we know that the y value is changing at a rate of 2 units per second. So there's a time measurement in there. So what we're looking for then is what is the dx dt. So as this particle moves along this curve, it's changing with respect to x, but it's also changing with respect to y. And we're looking for how is it going to be changing with respect to x when the dy dt is negative 2. So we're taking then our y equals 2x squared plus 1, knowing that y and x are both functions of time, and we're going to differentiate that with respect to t. So that's going to get us to dy dt equals, we have the 2 times, and then the chain rule on x squared is going to be 2x to the first times dx dt, and the derivative of the plus 1 is going to be 0. So we are trying to see that, what do we know? We're looking for, we know the dy dt is negative 2, so we can plug that in. And it left off too, we had another important piece of information that didn't come through on this. So we were looking for at what rate is x changing when, and my equation that I'm doing in Word isn't coming through here. So we said when x is equal to 3/2. It's kind of an important piece of information that we know that didn't show up on this document. So we have negative 2 is equal to, we've got the 2 times 2 is 4, and we were supposed to be given the information that x is actually 3/2, and then the dx dt is what we're trying to find. So we've got our equation down to where there's only one thing we don't know. So that's negative 2 is equal to, we can cancel there and get 6 dx dt. And so that means our dx dt, the rate of change of the particle in the x direction, is going to be a negative 1/3, and that's going to be in some unknown units per second. Okay, let's look at number 4. See what came through on this one or what didn't. So we have a person walks away from a 15 6-foot tall light pole. So you got this light pole up here, and this person is walking away. So the person is going away from the light pole. Of course, we can see the light coming down here at a rate of 2 feet per second. When the person is 10 feet from the base of the pole, we want to know first, how fast is the length of the shadow increasing? And secondly, how fast is the tip of the shadow moving? These are tricky questions here. So we're going to imagine that this person has a shadow. I'm going to make the shadow be black over here, but he's also got this distance that he is from the light pole. So we kind of need to name these things a little bit. We're going to call this distance right here, and we're going to call that x. We're going to say this length right here is the shadow, and this height of the light pole we know is 15. And it didn't come through here either, but the person is 6 feet tall. So the person is 6 feet tall. So this distance right here is going to be 6. So what we're trying to see is we have some similar triangles. We have the big triangle, and then we have the smaller triangle. And we know that the similar triangles the side lengths are proportional. So we can say that 15, I forgot one more thing we should say. We know that the person is moving away from the light pole at 2 feet per second, and we can now call that a dx dt. And in part A, what we're trying to find is how fast is that length of the shadow increasing. So we are looking for a ds dt. That is what we're trying to find. So in our similar triangles, we have 15 over x plus s. I have to be careful that that doesn't look like a 5, is going to be the same as 6 in the small triangle over just the s. So in a proportion, we know that the cross products are equal. So we can cross multiply and say 15s is going to be, and I'm going to distribute that and call it 6x plus 6s. So subtracting the 6s over, we're going to get 9s is equal to 6x. And I say maybe we can divide through by 3 and call that 3s is equal to 2x. Now both the s and the x are changing with time, so we can now take the derivative of this with respect to time. And so we're going to get 3 times the ds dt is going to be 2 times the dx dt. We're looking for the ds dt here, and we know that the dx dt is going to be, and I don't know that I wrote that, is going to be 2 because he's going away from the pole at 2 feet per second. So we are going to get then that 3 times that ds dt that we're looking for is going to be 2 times the 2 for the dx dt. And so solving for ds dt, we're going to get that that is going to be 4/3, and our units there are going to be in feet per second. So that's our answer to part A in this question. And then to try to answer the part B, what we want to know is how far is the tip of that shadow moving. So the tip of that shadow right here is at the end of this distance right here. So as the person is walking away from the light pole, then that's pushing that tip of the shadow out further. At the same time, that shadow itself is growing also. And so what we're looking for in the rate of change of the tip of the shadow is going to be the derivative of that x plus s distance. That is, it's going to be the dx dt, how far the person is walking away from the pole, plus the ds dt, the rate at which that shadow is lengthening. And so we have that that's going to be 2 plus our 4/3, or I guess we can call that 10/3, and that also is going to be in feet per second. So the fact that we were 10 feet from the base of the pole really didn't come into play at all. That is going to, the length of the shadow is going to be increasing at that rate regardless of how far we are. And likewise, the tip of the shadow is moving away from the pole the same regardless of how far away we are. All right, very good.